Hello, everyone. My name is Andy Kowles. I direct activities at the Storage Research Lab at the Zurich Research Center. My background is 23 years in storage, starting with hard drives at Seagate, also working on QLC and TLC SSDs at Micron. I also built the cloud with AWS for several years. Now I'm here. Let's talk a little bit about the innovations in our lab and generally. What we do in the lab is that we start with our current products. We also look at what's on the roadmap, but we're really looking at the N+2, N+3, what's out there that we can prototype, that we can theorize about, simulate, emulate, so that we can intercept the next generation of products, which is, really important. And also, Huawei is very good at this because of our vertical integration. Some challenges here, especially in this intelligence era. The throughput density problem. We've talked a lot about throughput, data-centric computing. As we add capacity, without adding bandwidth, we have the potential to strand capacity and make it inaccessible for services which have certain service level objectives and requirements. The growth of data, for example, LLM contexts, is explosive. Even for an HBM-enabled, very expensive NVIDIA or GPU complex, where HBM takes over half the cost of the complex itself, the working sets are overwhelming even that expensive memory. This causes inefficient data transfers, thrashing, excessive swaps, basically inefficient activity when it comes to the data. All of this leads into a very, very expensive problem, which is low GPU utilization. I challenge you to find high GPU utilization, or at least those who have invested in very large-scale GPU clusters are often disappointed by how much their GPUs are utilized. Let's just talk a little bit about media, because media is the key to storage. Media dominates latency, it dominates cost. There's clear differentiation between the media when it comes to cost and latency. Looking at latency in the context of data transfers, we can see that the transfer time can become large with large sequential runs. So depending on the workload, latency may or may not be your chief concern. Bandwidth instead is. So as bandwidth increases and transfer lengths increase, it can be possible to wave away a little bit the higher latency of some cheaper media in order to lower the cost of your system with no effect on the user experience. Keep in mind that in the GPU parallel computing era, even direct from memory, systems are designed to hide latency. So sequentialization is very important. Finally, NAND is a special media. We've long organized NAND for throughput. As interface speeds have scaled, throughput is able to scale because NAND is reorganized, parallelism is added at the die, channel, and PCIe lane level. So throughput density. Density increases without capacity increase. Capacity and density increases have outgrown interface, or for the same interface, as we grow the capacity, we lose throughput density. Again, this can cause stranding of capacity. If you see some of these examples, if I'm attached to an NVMe Gen 3x4 interface and I just add capacity, I have a degradation of throughput density. If I have the same capacity but I add interface speed, I can gain that scaling of throughput density. It's very difficult to scale throughput density. It requires brute force approaches like expensive buses, more expensive devices, which isn't ideal. So one of the things that we're working on in Huawei research is compute and storage acceleration. So basically, we're pushing the compute in this data-centric world, in this data-centric architecture that we envision. We're pushing the compute closer to the storage, either in the storage module, inside the SSD controller, or even on the media. What this does is free up data movement and increases what we call effective throughput. So for the same hardware, and we know hardware is very difficult to change once it's landed, for the same hardware, we can attain that ideal scaling of throughput density by increasing the effective bandwidth, basically transferring less data for the same amount of compute. In our research, we found massive acceleration can occur depending on where we put the acceleration, how close to the storage we put the compute. So throughput density and compute and storage acceleration go hand in hand. From an algorithms perspective, KV caches are highly compressible. They're often swapped very frequently. What we're able to do is attain high compression ratios on these KV caches and other AI-related metadata. What this does is increases effective throughput. What that does is allows higher throughput density for the same hardware. It also, by the way, lowers power, reduces wear on components, and frees up the CPU for additional compute. So another piece here is that because of Huawei's vertical integration, we're able to take research innovations, for example, new compression algorithms, and move them into silicon very quickly to get them out there into products to our customers with a rapid development cycle. Data and control disaggregation. We've seen some of that today with the appliances outside the door. Basically, we're moving away from a CPU-centric paradigm. We can linearly expand performance. We can end up with lower end-to-end tail latency because there's fewer stages in the data path. And this is available in the newest products. Another concept that is in our group we're talking about is NPO native I/O. Basically, the NPU becomes a first-class citizen in the system, which manages its own I/Os between media. Our storage provides an adaptive interface and semantics to cater to various needs. For example, block semantics, file semantics, vector, or object. This results in faster model training, reduced hardware, reduced inference latency, and a better customer experience, whether we're talking about inference at the edge or something in the data center. Again, this simplifies things by deleting components which are no longer centric to the customer experience. So, in this storage system, we have solutions. We look at solutions in our research group from rack scale all the way down to the disk. We have fully integrated compute, network, and storage solutions. We seek to maximize resource utilization, for example, GPU utilization, and uptime, and redundancy. We are working on minimizing blast radius, one failed component. How large is the blast radius for that component? We know that we want to minimize that. We also seek in the research group to allow field operability with field replaceable units as small as possible and hot swappable if possible. We're integrating our SSDs and our SSD technology in a low level with the GPUs and NPUs and DPUs. For example, in storage processing, where we add protocol that tightly couples the processing units to the storage such that offloads can occur. All of our innovations can be rapidly developed using custom silicon and our custom software ecosystem to provide rack scale solutions with the lowest TCO, the highest throughput density to all of the media that we may choose to attach. Current subjects for research, again, I mentioned throughput density. We're talking about not just raw physical bandwidth, but also effective bandwidth, essentially more efficient use of existing bandwidth. We're looking at NAND flash, new types of media, new configurations of that media that scale more efficiently. We know that at scale, tail latency is an issue, even if we're talking about very, very sophisticated and fast media. So we want, what causes tail latency? Well, errors cause tail latency, command collisions cause tail latency. And so things like protocols like zone namespaces and flexible data placement, research members of our group have either worked on those or conceived of these concepts. Also, error rates and failure prediction. Now, I use the P word, prediction. It's very difficult to do. But if you can predict, or at least infer, that a component is going to be slow or fail, you can steer traffic away from it, particularly in a vertically integrated solution. Multi-chip packaging. We might have heard of high bandwidth memory. What about high bandwidth flash? Basically, increasingly, the industry is moving towards 2.5D and 3D packaging, which requires serious innovation and the concept of decomposing SSDs, where we don't necessarily have a centralized SSD controller that controls many die, but rather we push some of that SSD sophistication down to the die level. Workloads. Conversations with customers in my career have always come down to workloads. What is the workload? Sometimes the customer doesn't know. Sometimes they do. Either way, our job, one of our charters in Huawei research is to characterize workloads, to obtain the workloads, to characterize them, and to look for opportunities such as sequentialization, such as data heat, and use those opportunities to design systems, which can be dynamic, to handle workloads in an optimum way. Finally, evolving interfaces. Throughput is key. Interfaces are becoming higher and higher throughput. For example, the Gen 5 to Gen 6 PCIe transition. We're talking about optical connections to allow longer run lengths of PCIe Gen 6, which is very difficult to run very far on copper. Compute Express Link. This allows coherent, large, pooled memory and storage across large distances. High bandwidth memory. High bandwidth memory is a completely new, completely order of magnitude higher throughput that we wonder, can we attach storage with high bandwidth memory? So all of this, again, is within the context of Huawei's vertical integration. We have native applications, we have a custom kernel in silicon, and we have a very broad product line. Our innovations from the research group are aimed at very quickly delivering into the products and then to the customers the value that we find in our research. That's all I had to talk about today. Thanks everyone for your attention.